In this episode, we're going to focus on encryption in a way that matches what cloud security actually demands, which is not just turning something on, but making sure it truly protects the data you care about. Beginners often hear that encryption is important and then assume the job is done once a service shows an enabled status. The cloud makes it easy to believe that, because many services provide default encryption and friendly indicators that sound reassuring. The problem is that sensitive data can still leak, be copied, or be accessed through weak permissions even when encryption is technically present. The goal is to think in terms of sane defaults, meaning secure choices that happen automatically without constant human intervention, and verified outcomes, meaning proof that the protection is real across data storage, data movement, and day-to-day access paths. When you approach encryption this way, you stop treating it like a checkbox and start treating it like a measurable control. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A useful starting point is defining what we mean by sensitive data, because encryption choices only make sense when you understand what you are protecting. Sensitive data can include personal information, payment data, credentials, security logs, internal business plans, or any records that would cause harm if exposed or altered. In cloud environments, sensitivity often depends on both the content and the context, because the same type of record might be low risk in a test dataset and high risk in production. That is why encryption strategy begins with classification, even if the classification is simple, such as high, medium, and low sensitivity. Classification helps you decide where encryption must be mandatory, where stronger key controls are required, and where additional verification is necessary. Beginners sometimes treat encryption as an all-or-nothing decision, but a more realistic approach is to apply consistent encryption everywhere while applying stronger key boundaries and stronger verification where sensitivity is highest. That creates a stable baseline without losing the ability to prioritize what matters most. Once you know what data is sensitive, the next concept is understanding what encryption actually provides in cloud platforms. Encryption protects confidentiality by making data unreadable without the right key, but it does not automatically prevent data from being accessed by an identity that is allowed to decrypt. This is the biggest beginner misunderstanding, because it leads people to think encryption replaces access control, when in reality encryption and access control must work together. Encryption can protect data if storage is stolen, if disks are copied, or if underlying infrastructure is compromised, and those are real threats. However, if an attacker compromises an identity that can legitimately read the data through normal service access, encryption alone does not stop that. That is why encryption must be paired with tight identity and access management, IAM, rules, and strong key boundaries. The right mindset is that encryption is a barrier against certain classes of exposure, while access control and monitoring are barriers against unauthorized use through normal pathways. Sane defaults are important because cloud environments change quickly, and the risk of relying on manual configuration is that manual work does not scale. A sane encryption default means new resources start protected without someone remembering to toggle a setting, file a ticket, or copy a secure template. When defaults are secure, the organization spends less time cleaning up misconfigurations and less time arguing about whether protection should be applied. This is especially important for services that teams create frequently, such as storage containers, databases, and messaging systems. If secure defaults are not in place, you often get drift, where the environment slowly fills with a mix of encrypted and unencrypted resources, and nobody can confidently say what is protected. Sane defaults also reduce the risk of accidental exposure during hurried moments, such as incident response or rapid product releases. The exam tends to reward the idea of secure by default designs because they reduce long-term risk by making the safest behavior automatic. At the same time, sane defaults do not mean trusting every default blindly, because defaults can vary by service, by region, or by the way a resource is created. One team might create a resource through a web console and get one set of default behaviors, while another team might create a resource through an automated process and get a different set of defaults. A service might encrypt data at rest by default, but leave data movement between components less protected if additional settings are not configured. Another service might encrypt data, but use a key model that does not align with your organization's expectations for ownership and separation. That is why sane defaults are not just what the platform chooses automatically, but what your organization defines as the baseline and enforces consistently. The idea is to make encryption outcomes predictable, so that anyone who creates a resource gets the same protection regardless of their method or experience level. Predictability is what makes verification possible later. A key part of encryption in cloud platforms is deciding how encryption keys are managed, because key control determines how meaningful the encryption barrier really is. Many services offer platform-managed keys that are convenient and often appropriate for baseline protection, but sensitive data may require stronger control and clearer ownership of key policy. This is where a key management system, KMS, becomes central, because it allows you to define who can use keys, who can administer keys, and how key usage is logged and reviewed. Beginners sometimes assume that using a KMS is automatically better, but the real benefit depends on how the key policies are designed and whether they enforce boundaries. For high-sensitivity data, you generally want key usage to be tightly scoped to specific application identities and environments, not broadly available to large admin groups. You also want key administration separated from key usage, so one compromised identity cannot quietly change policy and then exploit it. When key management is designed well, encryption becomes a stronger, more defensible control. Encryption also needs to be considered across the full data lifecycle, because data does not stay in one place. Data is created, stored, processed, copied, backed up, and sometimes exported for analysis, and each of those phases can create exposure if encryption is not consistently applied. For example, a database might be encrypted, but an export file might be created in a less protected storage location, and that export could become the real source of leakage. Backups can be even more dangerous because they often contain large amounts of sensitive data and are retained for long periods. A sane encryption approach treats secondary copies as first-class security concerns, ensuring that encryption expectations apply to backups, replicas, logs, and caches, not just to primary storage. Verification should include checking these lifecycle artifacts because attackers often target them as easier paths to data. When you think in lifecycle terms, you avoid the false comfort of encrypting the main system while leaving the supporting systems exposed. Another important area is encryption for data in transit, which is about protecting data while it moves between users, applications, and services. Data in transit risk is different from data at rest risk because it involves networks, endpoints, and connection behavior. A beginner might assume that cloud providers automatically protect all traffic, but there are often configuration choices that affect whether connections are protected consistently. Even when encrypted connections are used, weak settings or inconsistent enforcement can leave gaps, especially when services communicate internally. A robust approach ensures that sensitive data is not transmitted in plain text, that secure connection requirements are enforced where possible, and that exceptions are rare and controlled. This matters not only for external traffic, but also for internal service-to-service communication, because internal networks are not automatically trustworthy. The practical exam-oriented idea is that strong cloud security treats transit protection as part of the encryption story, not as a separate concern. Verified outcomes here include confirming that sensitive paths require protected connections and that misconfigurations cannot silently downgrade protection. Encryption can also fail quietly through permissions and access paths, which is why verified outcomes must include how data is accessed, not only how it is stored. If an identity has broad access to a service that returns decrypted data through normal requests, then the encryption barrier does not prevent that identity from accessing sensitive content. This is not a flaw in encryption. It is the reality that encryption must be paired with careful authorization design. Verified outcomes, therefore, include validating that only intended identities can read sensitive data, that administrative roles are limited, and that access is reviewed and monitored. It also includes confirming that data access does not bypass intended boundaries through indirect paths, such as exporting data, creating copies, or sharing resources. Many real incidents involve legitimate access pathways used by compromised identities, and encryption at rest does not stop those incidents by itself. The stronger design is one where encryption exists, key usage is controlled, and data access is constrained so that even if one identity is compromised, the blast radius is limited. Verified outcomes also require clarity about what you are verifying, because encryption claims can be broad and confusing. A service might say it encrypts data, but that could mean only certain fields, only certain storage layers, or only certain operational modes. Another service might encrypt data but allow configuration choices that switch encryption off for performance or compatibility, and those choices can be made accidentally. A good verification mindset asks precise questions like which data elements are covered, which storage and backup paths are covered, and which key is used, and under what policy. It also asks whether new resources inherit the expected encryption settings automatically, because a control that works only on old resources is not stable. Verification should be repeatable, meaning you can perform it regularly and compare results over time to detect drift. Beginners sometimes treat verification as a one-time confirmation, but the cloud changes too fast for that. Ongoing verification is how you prove the encryption story remains true month after month. An important part of making encryption defensible is connecting it to auditing and evidence, because real scrutiny demands proof, not confidence. Evidence includes records of encryption settings, key policies, and key usage logs that show how keys are actually being used. It also includes demonstrating that the organization can identify which datasets are protected by which keys, and that the key ownership and permissions match the sensitivity of the data. Evidence becomes especially important during incidents, when someone will ask whether exposed data was encrypted and whether the attacker could have decrypted it. If you cannot answer those questions with evidence, you end up with uncertainty that can expand the perceived impact and force broader, more expensive responses. A mature approach treats encryption evidence as part of normal operations, not as something assembled under stress. This includes retaining relevant logs, protecting them from tampering, and ensuring that key usage monitoring can reveal suspicious patterns. When encryption is evidence-backed, it becomes more than a technical feature. It becomes a control you can defend. Another practical reality is that encryption choices should survive operational pressure, because many security controls fail when teams are rushing. If encryption is hard to enable, or if it frequently breaks workflows, teams will find ways around it, sometimes without telling anyone. That is why sane defaults matter so much, because they reduce friction and reduce the need for special handling. It is also why key lifecycle decisions, like rotation and retirement, must be planned so they do not cause outages that lead to disabling controls. A resilient encryption strategy anticipates that systems will evolve, services will be migrated, and data will be moved, so it builds processes that keep encryption consistent through change. This includes planning how keys are managed during migrations and ensuring that sensitive data is not temporarily exposed in plaintext during transfer or staging. Even without describing implementation steps, you can understand that secure systems are the ones that remain secure when change is happening. A strategy that works only in perfect conditions is not a strategy you can rely on. Beginner misunderstandings often show up in predictable ways, and addressing them helps you avoid shallow encryption thinking. One misunderstanding is believing that an enabled status means the data is protected everywhere it exists, when in reality there may be copies, exports, backups, and logs that are not covered. Another misunderstanding is believing encryption solves access control, when in reality key usage and data access permissions determine who can see decrypted content. A third misunderstanding is treating key management as optional, when key policy and key boundaries are what prevent decryption power from spreading too widely. Beginners also sometimes overlook data in transit, assuming internal traffic is automatically safe, or assuming that secure connections are always enforced without drift. Finally, many beginners underestimate the importance of verification and evidence, thinking that once a control is configured, it stays configured, when in reality drift and exceptions are constant pressures. Addressing these misunderstandings moves you from encryption as a slogan to encryption as a control with measurable outcomes. When you put all of this together, Encrypting sensitive data in cloud platforms becomes a disciplined practice built on defaults and proof, not on assumptions and labels. You start by defining what data is sensitive and making encryption a consistent baseline. Then you ensure sane defaults so new resources are protected without manual heroics. You decide how keys are managed, using Key Management System, KMS, ownership and boundaries that match data sensitivity and reduce blast radius. You extend encryption thinking across the data lifecycle, including backups and exports, and you treat data in transit as part of the same protection story. You verify outcomes by checking coverage, key policy, access paths, and drift over time, and you preserve evidence so your claims survive scrutiny. Most importantly, you align encryption with real operational behavior so the secure path stays usable even when teams are moving fast. This is the mindset the exam is trying to build, because it proves you understand encryption as a living control that must be designed, enforced, and verified, not just enabled and forgotten.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.